Now we return again to the eclipsed conformation of ethane. The purpose of this particular model is to show where the vertical mirrors are in that particular molecule. Recall that we had said that the eclipsed conformation of ethane belongs to point group D3H. And we had seen that the high order rotation axis goes along this axis here. That's where the high order rotation axis is, the C3. Now we can see where the mirrors are, that the mirrors are not normal, they're not perpendicular to the high order rotation axis, and in fact they include the high order rotation axis. So that's why these particular mirrors are vertical mirrors and not horizontal mirrors. Again, we have, if we open up the molecule model on the inside, we can see the use of the dashes and wedges to show where the various substituents are relative to the plane of the paper. That the dashes here show the substituent is behind the paper. The solid line shows us that the substituent is actually in the plane of the paper, just as the two central carbon atoms are in the plane of the paper. And then if we come around to the front again, we see that we have the wedges. We're going to look back there, see the wedge pretty nicely. The wedge goes to this particular hydrogen substituent, which is closer to the student, is in front of the paper. So we can see again that if we look at the end of the molecule, we have a Newman projection, and we can look at it from either end of the molecule as helps us if we need to. So we have a Newman projection. We have a dash and stick type drawing that shows the relative positions of substituents relative to the plane of the paper. And we also have a model that's essentially to scale, that the relative positions of the hydrogens and the carbon atoms are very close to the experimental values. The values that I used were determined from a quantum mechanical calculation using a density functional theory method. And the last thing you may notice is, yes, I really do have man hands. Here we have another eclipse conformation, but with a slightly different substituent pattern. Here we have a 1122 tetrafluoroethane. So we have 2 fluorine substituents on the first carbon and 2 fluorine on the back. And they're arranged such that the hydrogen substituents are on the same side. So in this case, if we were to check for a C3 rotation, we would see that there is no C3 rotation. We would also see that we have a vertical mirror. So the vertical mirror goes along here, and we can see that it separates the left half and the right half of the molecule, and they actually are mirror images of each other, and which even continues slicing directly through the central carbon atoms. So we see that it does have a mirror. It turns out it has another mirror which is not demonstrated here, but there is a mirror plane that goes between the 2 carbons. And we would see, this model is not built to do it, but that if we were to put a stick through the model, that it actually has a C2 rotation. So the high order rotation axis for this particular molecule is C2, and since it has 2 vertical mirrors along with the identity, we would recognize that this particular molecule belongs to the point group C2V. Here we have a slightly more complicated substituent pattern. Here we have a fluorine and a chlorine atom on the front carbon, and likewise we have a fluorine and a chlorine on the backside. So we're still dealing with eclipsed conformations of ethanes. So in this case we have a 1,2-difluoroethane, an eclipsed conformation. Now in this particular case, if we were to look along this particular line, we would notice that we don't have a vertical mirror, because if we did have a vertical mirror, it would mirror fluorine into chlorine, and that doesn't work. Hydrogen goes into itself, that's not a problem. We might also look for a mirror plane going from here to there. But if we had a mirror plane along this particular line, it would take a fluorine atom, which is that fluorine, into chlorine, and that doesn't work. So we see that we have no mirrors, but we do have an interesting symmetry operation. We have a C2 axis, and we can model a C2 axis putting a wooden skewer through our model, and we notice that we start with fluorine. Notice we have fluorine on the left side, chlorine on the right. Now if I rotate it by 180 degrees, it brings me back that I have fluorine on the left side, chlorine on the right side. So this shows us that this particular molecule has a C2 rotational axis. And we have a very nice way of demonstrating exactly where it is by using one of these wooden skewers. Not only does it demonstrate the C2 operation very well, but if you're attacked by very small vampires, you're in luck. So this will show this particular symmetry operation. So since the only symmetry operations this particular molecule has are C2 and the identity, this is a point group which we hadn't previously encountered called C2. Not C2V because there's no vertical mirror. It is not C2H because there is no horizontal mirror. We just have C2 and that's it. And C2 is a perfectly good point group for a molecule to belong to. Since we had been mentioning various C2 rotational axes in these eclipsed ethanes, I thought it would be a good idea to go back and look at our parent compound, ethane itself. And recall that we had noticed that along this particular axis, we have a C3 high order rotation axis. So I've slightly disassembled the molecule, the model, to show that where the C2s are. Recall that since this belongs to D3H, the fact that it is a D group, the big D in the front, tells us that we must have 3 C2s that are perpendicular to the high order rotation axis. And again, recall that the high order rotation axis goes right along there. Well, here is one of the C2s. It's the other skewer that I'm holding with my left hand. And we can see that they really are perpendicular to each other. So let me show first that this really is a C2, that it really acts as a C2. Well, if we hold it this way, and we make a 180-degree turn along this particular rotational axis, we see that we have exactly the same arrangement we had before. We have 1 hydrogen at the top and 2 side by side at the bottom. So that really is a valid C2 axis. And we can go through this model and actually, you can find them. Find the hole is a little tricky at times, but there it goes. Here's the another of these C2s. This is the second C2. And again, we can rotate it by 180 degrees. And we see that we get exactly the same arrangement that we had before. And then there's one last C2, which I'll put in here. Comes in the side. That's right, there we go. Yeah. So this is the third one. So we have our third C2, and we can rotate by 180 degrees. We get the same arrangement that we had before. So therefore, we've been able to find all 3 of the C2s. So we can kind of put in at least where the C2 starts. That's where another one starts. And then the third one is in this direction. So the nice thing about these types of models is you can actually, it's one thing to imagine where the C2 axes are going to be by looking at a picture that is drawn on a piece of paper. It's quite another thing to actually be able to visualize it in 3-dimensional space and be able to actually move the model around and see, oh yeah, it really does what it's supposed to do. I can actually see it. And I think that helps reinforce for the student much more clearly the reality of these particular symmetry operations, and makes it much easier for the student to recognize where these particular operations are going to be in a molecule that they may not have encountered